Marine, thank you very much for your presentation. And now we move on to the next presentation, which will be given by Delphine Vantelon, who is Beamline Manager of LUCIA Beamline at Soleil Synchrotron. And she will be talking about chemical imaging and speciation in the tender X-ray domain at this beamline. So please, the floor is yours. Could you please switch on your microphone? We cannot hear you. We can see your presentation, but we cannot hear you.
Yeah, can you hear me?
Yes, now it works. Okay, thank you very much.
Yeah, sorry, I made some mistakes with the screen sharing. And so now you should be able to see my laser pointer. Yeah, so thank you very much for inviting me to present the LUCIA capabilities and the specificities to this workshop. And maybe it will have a little sisters in Solaris, so I understood. Yeah, so LUCIA, I will present you these capabilities, but also LUCIA is the team, and which is composed by Damien Roy, who is our assistant engineer. We are 4 beamline scientists, Camille Rivard from the INRAE, Nicolas Tresserra, Bénédicte Lassalle, and myself. And currently the staff is complemented with Pierre Lagarde in Emeritus and Anna Pradas as a postdoctoral fellow. So, LUCIA is the tender X-ray beamline of Soleil dedicated to element mapping and speciation by X-ray fluorescence and X-ray EXAS coupling. So it means that we are working in the 0.6 to 8.5 keV energy range, and the beam can be as large as 2.5 millimeter or focus down 2.5 micrometer. Then in this case, we can map in an heterogeneous sample, we can map the elements that are reported in this Mendeleev table. You can see an example of map here, and on specific location of the map, we can collect the XAS, either XNS or EXAFs, to obtain the speciation of the element, its oxidation state, and electronic and atomic local environment. And this can be done on samples, as you will see, that are super heterogeneous, so some liquid, solid, or ordered or amorphous samples. And the detection limit is rather low because of the fact that we are on an undulator, the source is an undulator. And also to cover the whole energy range, the beamline has a monochromator that is composed of a DCM, with several crystals and a multi-layer grating monochromator to cover the low energy range. And it is working with this focusing mirror and an exit slit after the monochromator. And then the beam can be focused, translating KB mirrors into the beam as the last mirrors optics of the beamline. And so you can translate them into the beam or remove them to the beam. To have the focus of the macro beam size, and then the beam enter into the experimental chamber. You have a picture here of the permanent experimental chamber and an image of the inside of the chamber here. We have 3 methods of detection that can be used together. A fluorescence detection with a 60 millimeter square SDD currently. We can measure also the current of the sample, and then we get the total electron yield. And we can also measure transmission, if possible, using a silicon diode installed on after the sample. We also have 2 movable vessels that can be installed behind the permanent one. One that is under UHV, sorry, for surface science, and one that we are currently still in, building, but still it is already usable, but not really complete, which is dedicated to operando in situ experiment and liquid cells. So the samples, as I said, they can be numerous, liquid, mud, solid, can use powder and deposit them on carbon tape or pressed into pellet. We can work on massive samples or thin sections that can be cryogenic, freeze-dried, or embedded into resin. We can work on cells. And I will show you on complete little specimens. They can be able to enter into the little space of the vessel, as yes, I have to mention that the constraint is that we are working under vacuum because we are working in the tandem X-ray domain. So then the samples are installed on copper plates with variable design adapted to the different samples we can measure. And also we have developed some sample environments compatible with the vacuum to work on the samples under constraint, such as the temperature constraint or pressure. For temperature, we have a furnace, but we also have a helium cryostat on which we can set the energy, and then you can study phase transitions with a low temperature. And we are also currently working on the homemade reaction cells for microfluidic or electrochemistry operando experiments. Then, as all XAS beamline and as ID21 and also microXAS, LUCIA is welcoming users from many scientific communities. The main one on LUCIA are from geoscience, environment, and material science, with overlaps, of course. Also, we have an increasing community coming from biogeochemistry and health science and chemistry demanding operando measurements. And we have a continuous little number of teams working on surface science, and we receive few proposals from cultural heritage, certainly because they are all going on ID21, but we have some sometimes. And then I will give you, in fact, a quick overview of all the experiments, the experiments we can perform on such a tandem X-ray beamline. For geoscience, environmental, and biogeochemistry, I will use metals to make a sort of common thread. Then on the metals, when they occur as naturally in the environment, but then when they are waste from human, and then after the waste and transfer, what happens when they are ingested by living organisms. Then I will switch to the study of materials with materials for catalysis, just the study of the structure and the structure during operando functioning. And also what we can do under constraint with pressure and temperature, and I will finish with surface science. Yeah, so in this case, on geoscience, our users wanted to study the evolution of the scandium speciation during the alteration process in a profile depth from the parent rock to the surface. So they collected samples at different depths of the profile, and they measured the scandium K edge xanes, and they used them as a fingerprint to follow the scandium modification, the modification of the scandium speciation and its evolution with alteration. And they also use calculation of xanes, for example, in this case of scandium linked to goethite, to really decipher if scandium is adsorbed or introduced into the goethite structure. That would have some consequences of the scandium availability. Then when the scandium heavy metal is extracted, it is used in metals and, for example, in plastics. And here is an example of what is inside a plastic altered, weathered, collected on a beach. Here you have an image, an XRF image of the section. You see the cracks at the surface of the plastics and all the metals that, part of all the metals that contain the plastic, some of them being toxic. And so clearly with the alteration, you see here at the hotspot of chromium, with the alteration, you have a release of these toxic metals into the environment and performing xenes and hexaps at the chromium edge in different locations of the map. Users could observe that chromium occurs in this sample as a chromium-3 linked to the polymer of the plastic, but also as a cobalt chromite nanoparticle, and also as chrom6, which is the toxic form of chromium, as associated with lead in crocoite, or with potassium as a chromate potassium. So then the plastic weathering, as said, released the toxic metals in the environment. And then when it is released, it is transferred in the hydrosphere and can be trapped by colloids. And here is a study of a structure of colloids and how it evolves with the variable physicochemical parameters where it is sitting. Here the study is the evolution of calcium concentration. So when calcium concentration, so then when there is calcium interact with the organic matter, forming dimers, bridging the organic matter. And this was demonstrated by the hexaps at the calcium KH performed on the different colloids. And then when calcium bridge the organic matter, you have an increase of the size of the overall colloid that settle. But also you have a liberation of the sites at the surface of the ferrohydride that can grow up a little bit, but also trap more metals, such as arsenic, that has affinity with this ferrohydride. So in this case, the colloid traps more arsenic and immobilize it at in the sediment of the water system. Then metals can be ingested. Here is a study of the ingestion of colloidal silver suspension by mouses and what happens in the colon of these mouses, as the users have demonstrated that the colon is damaged by this ingestion. And here you have an image, XRF image of the section of the colon. And you see with the map of silver and sulfur that they are colocalized, and with the xenes at the silver edge, that in fact the silver changes its speciation to form complexes with the tiol groups of protein or peptides. Here is an additional study on the effect of ingestion of rare earths and the toxicity of daphnia, because here, as you can see, we could study the whole specimen, that it is small enough, and with sulfur you follow the organisms of this daphnia, and here you have the location of the lanthanum in the intestinal tract. And here you have the distribution of the gadolinium, which is now in the tissues. And the users observed that the gadolinium was more toxic than the lanthanum. And here we could observe that it is localized in the organisms of the species, in the tissues. Yeah, now I switch to material science. And so here is the study of the ex situ study of what happened during the synthesis of the cerium oxide that can be used in catalysis, either as support or as an active phase. And so these users could see that during certain processes of synthesis, they could reveal an unexpected phase of cerium hydroxide with the cerium LH xenes. With this phase is this one in green, and then they could determine the structure formed, the intermediate structure form that can have an impact on the final phase, its stability and its efficiency according to the synthesis protocol people can use. Then I show you two examples of in situ modification of materials under constraint. Here is under high pressure in an anvil, in a diamond anvil cell that is dedicated to LUCIA, as it allows to use thin diamond to allow the transmission. And so here we can reach 50 gigapascal. And here you can see that with the EXAFs, they could see that above 45 gigapascal, they observe the symmetrization of the iron octahedra. And with the XANES and the FDMNS calculation, they could observe a high to low spin crossover of the iron 3+, also above 45 gigapascal. Now I switch to the modification under temperature, here of nanotubes of imogolite. And so we use a furnace up to 800 degrees Celsius. And so the users followed the transformation of the nanotube of the imogolite to layers which with a mullet-like structure. And during the heating in situ, they could observe the transformation of aluminium with the XANES from octahedral organization to pentahedral and then tetrahedral. I have to mention that this was measured with macro beam. So macro beam has also an interest, not only micro or nano. And so now here a report of one of our first operando observation of reduction of CO2 with the catalyst that is iron tetraphenyl porphyrin, studied at the iron cage, so with a homemade electrochemical cell. And so following the iron speciation with the XANES, they could determine the modification of this TPPC, I think they call that, during the catalysis. And also they could determine the structure that is in orange here, that the reduced species, that is the active form of the catalyst during the catalysis. And then I finish with surface science. These users could follow the arrangement of silver clusters on different surfaces, magnesium and magnesium oxide and aluminium oxide, and in fact depositing different layers and amount of silver on the surface. They could observe that below 3 nanometers of particle size, then the silver is forming monolayers. They followed it with the EXAFs of silver. They form monolayers, and which distances, furthermore, IgIg distances in the cluster is controlled, is determined by the lattice of the support. Here, magnesium oxide, and here, aluminium oxide. With the magnesium oxide, there is for very low deposit, there is a weak bonding that allow the constraint to be removed. And then above 3 nanometers, the silver coverage is high enough to allow the formation of 3D clusters in which the AgAg distances are the one of bulk silver. Voilà. I have finished the quick overview of the examples of science we can perform on the line. And then to finish, I will also remind you that in the tender X-ray domain, we can work on numerous types of samples with many scientific applications, and we can develop many samples of environments, just taking into account that we are working under vacuum. And in the case of LUCIA, according to the evolution of the demand of the beamline, the users are demanding for more in situ operando experiments. So we are currently developing the fly scan also for the EXAFs on the whole energy range, and we expect to have it to provide it to users in 2025. Also, they are asking for better spatial resolution, and we are working on building a new experimental station with a beam size at around 500 nanometers, also ready in 2025, we expect. And then with Soleil 2, in 2030, I think, we will get higher flux. Furthermore, we will move, so LUCIA will move and change its undulator to a more to a one that will give more energy, more flux, sorry. And I thank you for your attention.
Thank you very much for this very impressive presentation and showing us the research capabilities of LUCIA beamline. Do we have any questions? Look, Patty, please.
Hello, Delphine.
Hello.
Thank you for your presentations. Nice to see the evolution from LUCIA. I have a question. I would like to understand, actually, from your point of view, actually, what are the impact or the developments on samples which are related to magnetismus? I mean, your beamlines can go fairly down and approach really important edge, which are relevant for magnetismus. But do these things still active, or how is it regarding to the rest of the landscape of the research? Can you comment?
Yeah, there is a beamline at Soleil dedicated to magnetism study.
No, but for at LUCIA, you have also this capability, right?
Alors, well, we have, due to the undulator, we have the possibility normally to perform circular or linear variable polarization. When they build up the undulator, at one point we had to select either we want to a linear polarization or a circular polarization, because if they improve one, it was at the expense of the other one. So because there is a beamline dedicated to XMCD at Soleil, we didn't take this option. And I have to mention that we have the option for variable linear polarization that almost nobody asked for. That's why in far future, but with Soleil 2, the machine staff proposes to have another undulator without this possibility, because in fact it was not used. So we don't have this this magnetism community at LUCIA, in fact, at the end.
Okay, thank you.
I do not see any questions. There is still the possibility to write in a chat. Even later on, you can just write in a chat your question. Yeah, we do not have more questions. So Delphine, thank you very much for your wonderful